Why does the ball come back to you every time you kick it towards the wall? Looks like the wall is kicking it back to you, doesn't it? The speed of the return of the ball also differs based on the force of the kick aimed at the ball. Actually, the wall exerts a force on the ball to return it to you. This force is a reactive force and is induced by your action, that is, kicking the ball to the wall. What happens when you try pushing a wall? It pushes you back in reaction. Newton's third law relates the reactive force to the force applied on a body. In this lesson, you will learn about the third law of motion and conservation of momentum. At the end of this lesson, you will be able to state Newton's third law of motion, explain the law of conservation of linear momentum, and identify the situations where this law is observed in daily life. Newton's third law of motion, also known as the law of reactive forces, states, when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects but never on the same object. According to this law, if we push an object, it pushes us back. And if we pull it, it pulls back with a force of equal magnitude. Let's revisit the situations we observed at the beginning of this lesson. The boy kicks the ball to the wall, say, with a force of 10 Newton. The wall kicks the ball back with equal force. The direction of the force exerted by the wall is opposite to the direction of the boy's kick. One force acts on the wall, while the other force acts on the ball. In the second situation, the man pushes the wall with a force, say 100 Newton. What happens to the wall? The wall also pushes back with a force of equal magnitude. Both these forces act in directions opposite to each other. And one force acts on the wall while the other acts on the man. Let's verify this law using two spring balances, A and B. Spring balance A is fixed to a wall with the other end hooked to spring balance B, as shown. When a force is applied on spring balance B, it also stretches spring balance A. Observe the readings on both A and B. Both springs show equal expansion, indicating equal magnitude of force on the springs. The direction of expansion of spring in A is opposite to that in B. And as you pull B, its spring expands due to the applied force. Since A and B are hooked to each other, B exerts force on A, expanding the spring therein. You can say A is reacting to the pull force on B. Here, the force due to B is exerted on A, while the force due to A is exerted on B. To put it simply, the essence of the third law of motion is that every action has an equal and opposite reaction. Here, action and reaction refer to the applied force and the reactive force. This means action and reaction always occur in pairs. For instance, consider a boxer punching the sandbag. The sandbag seems to be punching the boxer back. Thus, force exerted by the boxer and the force with which the sandbag hits back form a pair. Let's examine some other situations where this law can be observed. If you push a spring fixed to a metal block with a force F, the spring pushes against your hand with same magnitude of force, that is, F. Let's now examine how this law applies in the case of a collision. Suppose two trucks, one big and another small, are involved in a front-rear collision. One would think only the small truck would suffer damage. However, that's not quite true. As you can see, the bigger truck also suffers damage. This is because when the bigger truck hits the small truck also hits back with a force of the same magnitude. Hence, there is damage to the bigger truck. The functioning of a lot of applications we use is based on Newton's third law of motion. Let's look at a few examples. Blow a balloon and release it without tying up the opening. The air inside the balloon escapes downward through its opening. The escaping air exerts pressure on the balloon, providing a thrust to the balloon and pushing it in the direction opposite to the direction of the escaping air. Here, the escaping of air can be regarded as the action. The motion of the balloon in the opposite direction is the reaction. Thus, the reactive force of the escaping air keeps the balloon afloat in the air till the air in the balloon is exhausted. Jet engines also work on a similar principle. A jet engine pushes air backwards during flight. As a reaction, the aircraft is pushed forward. If you like swimming and diving, you must be familiar with diving board. During a swimming event, a gymnast hops on the free end of the diving board before jumping off. The hopping action pushes the board down. When the board is released, it pushes the gymnast up in reaction. The reactive force enables the gymnast to jump higher. This shows that every action force is matched with the reaction force, which is equal in magnitude and opposite in direction. In the third law of motion, you see two equal forces acting simultaneously against each other on two objects when an event such as collision occurs. However, according to the second law of motion, the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction of the applied force. This means that during a collision, the rate of change of momentum of one object is related to that of the other, since the force exerted by both the objects is equal. However, the sum of the momentum of both the objects before and after the collision remains constant. Hence, in the absence of any external force, the total momentum of the system is conserved. This is known as the law of conservation of momentum. In this lesson, we will focus on linear momentum. Therefore, the law of conservation of momentum in this lesson actually refers to conservation of linear momentum. To understand this law, consider two spheres, A and B, of mass MA and MB, moving along a straight line. A is following B, and both these objects display unequal initial uniform velocities. Let these velocities be UA and UB respectively. The magnitude of velocity of A is greater than that of B. Momentum of an object is the product of its mass and velocity. Therefore, the momentum of each sphere is mass times its velocity. Assuming there are no external forces, the total momentum in the system will be equal to the sum of the momentum of both the spheres. Since the spheres are moving to unequal velocities along the same path, they will collide at some point. Let's assume that after collision, both the spheres A and B move with uniform velocities VA and VB respectively, in the same direction as that before collision. As the spheres move along a straight line before and after collision, their momentum is said to be linear momentum, we can use the second law of motion to find the relationship between the momentum of the spheres before and after the collision. According to the second law of motion, force is proportional to the rate of change of momentum. Upon collision, the force exerted by A on B, FAB, is equal to MB multiplied by VB minus UB divided by T. Similarly, the force exerted by B on A, FBA, is equal to MA multiplied by VA minus UA divided by T. According to Newton's third law of motion, these two forces are equal in magnitude and opposite in direction to each other. Here, FBA is the force of action while FAB is the reactive force or reaction. Since it is a reactive force, it is always indicated with a negative sign. By equating both these forces and simplifying the equation, the sum of the initial momentum of both the spheres before collision is equal to the sum of their final momentum after the collision. Hence, we can conclude that the total momentum in the system is conserved. You can observe the phenomenon of the conservation of linear momentum in a variety of everyday activities. For example, look at Jim getting off the boat. While jumping out of the boat onto the pier, Jim loses balance and falls into the water, as if someone pulled the boat back from under his feet. This is because when Jim exerts force to jump out of the boat onto the pier, he pushes the boat backward in reaction. Thus, you can see Newton's third law of motion at work. When Jim is in the boat, the total initial momentum of his body and the boat is zero. In jumping out of the boat, he exits that system using some momentum. Equal momentum is conveyed to the boat pushing it back. This is how Jim falls into water. Similarly, consider the example of a cannon. When a cannon is fired, the cannonball shoots off with a very high velocity. Since the force exerted by the cannon on the cannonball is equal to the force exerted by the cannonball on the cannon is pushed back in recoil. If the vanes of the cannon are not locked, the momentum due to recoil makes the cannon roll backwards. The law of conservation of momentum, formulated nearly 3 centuries ago, is an inference from a large number of observations and experiments. It is interesting to note that not a single situation observed so far contradicts this law. This brings us to the end of this lesson on the third law of motion. In this lesson, you have learned about Newton's third law of motion and the law of conservation of momentum. Let's quickly summarize the 3 laws of motion. The first law states that an object will remain at rest or continue to move at a constant speed in the same direction unless an external force acts upon it to change the state. Newton's first law of motion gives the concept of force. The second law states that the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction as that of the applied force. Newton's second law of motion gives the measurement of force. The third law states that every action has an equal and opposite reaction. Newton's third law of motion gives the application of force. The section on solved problems provides you an opportunity to review a model problem based on the third law of motion. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.